Hello everyone, this is Han Jung, and I am one of the co-first authors of this paper, LiDAR-UDA. I will briefly explain our paper in this presentation. To begin with, autonomous driving relies on LiDAR segmentation methods that recognize the objects and scenes from the 3D point cloud. However, LiDAR segmentation methods usually struggle to adapt to new domains due to domain shifts. The domain shifts are often caused by different environments, but LiDAR segmentation poses a unique challenge here, the sensor configuration difference. For example, as shown in the left figure, one dataset has much denser LiDAR beams compared to others. Also, the sensor orientation and location may change depending on which platform you use, as shown in the right image. Those domain gaps aggravate the LiDAR segmentation performance when it faces a new environment or a new platform. Thus, solving this problem is essential in robotics community. In our work, we propose novel self-ensembling modules based on the self-training scheme. We apply within-frame ensembling to simulate the beam pattern difference in different LiDAR sensors, and also apply cross-frame ensembling to refine the predicted pseudo-labels by using temporal information. We iterate the pseudo-label generation and student model training for n times for adaptation. We want to note that the within-frame ensembling only applies once at the beginning of the adaptation process. For source model training, we apply structural point cloud subsampling to simulate the beam pattern difference when the source dataset has more LiDAR beams than the target dataset. Let's say the source dataset has 64 LiDAR beams and the target one has 32 beams. Then we randomly drop the half of horizontal rows of source point clouds to match the number of beams in the target dataset for training. As shown in the figure, it effectively simulates the beam pattern difference. During adaptation, we apply within-frame ensembling based on the structural point cloud subsampling for pseudo-label generation. This is to match the number of beams in the target dataset to the source. We apply this subsampling n times and average predicted pseudo-labels of each point. And then we apply cross-frame ensembling to refine the pseudo-labels by using temporal information. With a given point cloud at time t, we aggregate the point clouds within a certain time window t from the past and future. Then we calculate an epsilon ball of each point and apply learned aggregation model to predict the averaging weights. Finally, we weight average the predictions to get the refined pseudo-label. The k-nearest neighbor algorithm can also be used for aggregation, but LAM brought more performance gain in our ablation studies. Here is our experimental results. As shown in the left table, ours significantly outperforms existing baselines in kitty to nuisance and nuisance to kitty experiments. Also, the tables on the right show the effectiveness of our structural subsampling, cross-frame ensembling, and LAM. Each module improves MIOU by a large margin. We also compare our method on other adaptation scenarios. We measured adaptation performance on kitty to USL and post datasets, and post to kitty and USL datasets. In every scenario, our method outperformed the baselines and source models. Finally, we visualized the predictions from the kitty to nuisance adaptation scenario. As shown, applying cross-frame ensembling with LAM successfully finds pedestrians, while using KNN or not using any ensembling modules fail to correctly identify them. This is the end of the presentation. Please come to our session or visit our project page for more information. Thank you.